So hi. As promised, here's the lecture to about the normal forms. I thought that instead of going through what we missed, just go through all the normal forms again as a recap. As we mentioned in the lectures, that this is the actual portion that we determine how good or how bad the normal forms are. So we will be going through the 4 different types of normal forms: the first, second, third, and Boyce Court normal form. And then after that, I'll show a few examples. And finally, I will show you all how to either decompose or construct databases so that they will be definitely conforming to either the third normal form or the BCNF. Okay, let's go ahead now and do what we need to do. So do a recap. What are prime and non-prime attributes? Prime attributes are attributes that are part of the primary key, and non-prime attributes, they are not part of the primary key. So if we take into this relationship A, B, C, D, E, F, and the following functional dependencies: C to F, C to F, E to A, EC to D, A implies B. The primary key that we get from, or rather the candidate key that we get from this relationship is what we first carry out what is missing from the right hand side. We get CE. When we find the closure of CE, we get all the attributes A, B, C, D, E, F, and so we can conclude that CE is a candidate key. And because of that, we can then say that CE is a prime attribute, and the non-prime attributes are the rest of them, which is A, B, D, and F. Okay, this will be critical when we are doing the first, second, third, and BCNF normal forms. So let's start with the first normal form. We can say that the database or the schema is so-called conforms to the first normal form if it follows these few criteria. So if the elements in the domain are indivisible, so that's the first thing. And let me check. And then all the values must be on the same type. So meaning that I missed this out the last time. So all attributes must be of the same type. So I can't mix between strings or integers, so they must be all the same type. Every column must have a unique name, and finally order does not matter. So these are the 4 different conditions required for something to be of first normal form. As you can tell, it is pretty typical for so-called your database to be of first normal form. Your Excel tables typically will be of the first normal form as well. We have an example below that does not conform. For example, these are merged cells, so this will not be atomic, because definitely yeah. So if they are together, Star Wars repeated for every row, then that will be atomic. The second thing will be this, whereby I'm mixing between addresses, so this will also not be a first normal form. So I think we discussed a little bit on this in the earlier part of the course. So this will not be considered as a first normal form. So yeah, what then will be the second normal form? In the second normal form, it has got to be first in the first normal form. So that is the criteria, and every non-prime attribute must be fully dependent on the candidate key. Perhaps this is not good. On a candidate key. So the official term for this is called partial dependency. So there is no partial dependencies on it. So for an example, in this table that we see over here, So we have title, year, and the star as the primary as the candidate key. And let's say if I have certain functional dependencies, title year to studio, studio to address, following. Title year implies studio will violate the second normal form because it is only on the left hand side. It only contains part of the candidate key. So if it contains title, year, and star, then it will contain the full candidate key, and so it will be at least of the second normal form. In this case, this is not in the second normal form. As you can tell, we have edited the tables over here a little bit, and so this will be in the first normal form. All the individual rows are atomic, and then we also don't have so-called the so-called the columns here. It's also atomic as well. But this is an example whereby it is not in the second normal form. Okay, this is the example that we did earlier. Let's look at this example. If I have a relationship A, B, C, D, E, and A, B, D implies C, B, C implies D, C, D implies E. So we find that AB is not on the right hand side, so we find the closure of AB. And closure of AB is just AB, so it will not be a candidate key. So we have to expand out what are the other variables that may come in to become the candidate key. So we have to try with both C and D because they appear on the left hand side. So ABC will give me the closure of ABC will give me ABCDE. The closure of ABD will also give me ABCDE. And so both ABC and ABD are candidate keys. And when we have these candidate keys, we find that both these two functional dependencies, they will violate that of the second normal form, because on the left hand side we have BC. It is only a part of my candidate key, so it fails the partial dependency criteria. So in this case, BC implies D and also CD implies E. Both of them violate the second normal form. Okay, now let's look at the third normal form. In the third normal form, we talk about transitive dependency. So transitive dependency means that every non-prime attribute depends only on the candidate key or the super key. So it must, of course, it must first be in second normal form, but the second criteria is every non-prime attribute depends only on the candidate keys and not on the depends only on the candidate keys or the super key. So let me provide an example. So naturally we know that this is already not in second normal form, but let's look at this functional dependency. So studio is not a candidate key. Studio address is a non-prime attribute. So this non-prime attribute is dependent right now on a non-candidate key, or rather this is a non-candidate key, and so this would violate the third normal form. Let's look at an example. If I have a relationship A, B, C, and A implies B, B implies C, the prime attribute is A, the non-prime is B and C. So this would disrupt the third normal form so-called criteria. Another example we have over here, R is A, B, C, D, E, and let's assume if A implies B, A implies C, DE implies C, DE also implies B, and C implies D as well. On the right hand side, the attributes that are not there is A and E, and we find the closure of A and E, which is A, B, C, D, E. We find that AE is hence a candidate key. The prime attributes are AE, and the non-prime attributes are B, C, and D. Okay, let's look at this example. We find that A implies B and A implies C. It is a non-prime attribute that's dependent on part of the candidate key, which is A. And so by default, this will violate the second normal form. So if it violates the second normal form, so regardless, it will hence also not be in the third normal form. Let's look at the definition of second normal form. Second normal form, non-prime attribute is fully dependent on the candidate key. And in this case, we find that the non-prime attribute, which is both B and C, they are dependent on only part of the candidate key, which is A. And so this would violate the second normal form. Okay, third normal form, it's always possible to so-called create a table that is of third normal form. This is an example whereby if you create it, you may end up with so-called you may have some so-called maybe lossy, but later on I'm going to show you a method to create third normal form tables whereby you are guaranteed to be lossless and preserving of all the functional dependencies. So we'll do that later on during this lecture. The last one that we are going through is Boy's court normal form, BC and F. So in BC and F, there has one additional restriction over the third normal form. So firstly, it must be in the third normal form, and the additional restriction is that all the functional dependencies must have a super key on the left hand side. So this is the main so-called criteria for BC and F. Okay, in this example, we have R is A, B, C, D. We have the functional dependencies. A is to implies BCD, BC implies AD, D implies B. And so the key in this case is A, B, and C. Okay. Maybe at this point of time, I want to point this out, especially for this example. So we realize that for A, B, C, D, in this functional dependency, we don't have any, or rather, all A, B, C, D attributes all have appeared on the right hand side. So usually, or rather, so far, all the examples I've shown have at least one attribute that does not appear on the right hand side. So when you want to find the candidate key, you can just build upon it from there. But in this case, you realize that all the attributes have appeared on the right hand side. So when you're trying to build this candidate key, you are in fact starting from a null set. So when you start from the null set, you have to iterate through all the attributes. So you first have to iterate through A. You find the closure of A, and the closure of B, the closure of C, and the closure of D. After you have found the closure of A, or rather in this example, after you found the closure of A, you realize that A is a candidate key. Okay, so good. You put it as a possible candidate key, and you try to find closure of B. You realize that B only implies itself, so B is not the candidate key. You do with C as well. You realize that C also only implies itself. It is not a candidate key. D will imply only B and D itself, so it is also not the candidate key. However, we will not be able to just discard away B, C, and D just like that. Why? Because we need to check if there are any elements with candidate key of two attributes. So we need to also check whether is BC a candidate key, is BD a candidate key, and is CD a candidate key or not. So in this case, we have to check for all those other elements, And over here we find that, let's look at BC. We find that BC and we try to find the closure of BC. For the closure of BC, we find that BC implies AD, and yes, BC is also a candidate key. Okay, let's try with BD. BD will imply B and D itself, so BD will not be a candidate key. Let's try with CD. So in fact, CD will also be a candidate key, because CD will imply CD, D will imply B. Oh, sorry, CD will not be a candidate key because there's no A. So CD will imply just C and D. D implies B. So A is missing, and so CD is also not a candidate key. So the only candidate keys in this relationship is A and B, C. So please take note of this. Why? Because it's just a little bit different from the other so-called examples we have seen so far. So in this particular example, I repeat, you have all your attributes have appeared before on your right hand side, and so you are left with a null set when you are trying to build up the candidate keys. So this is one point that you want to really take note of. And okay, so back to this example. In the BCNF, you have the keys of A and B, C, and you realize that D implies B will violate that of the BCNF. Okay, so now let's look at one example. So we have relationship 1 and 2, or schema 1 and 2. So the first one is A, B, C, D, E, F, and the second is E, G, F. And you have the following three functional dependencies. From this, we find that R1 is A is a candidate key, and for R2, maybe let's go through this. For this, the right hand side is missing A. We find the closure of A, and we find that A implies A, B, C, D, E, F, and so A is a candidate key for R1. For R2, F is missing from the right hand side, and so we have to find the closure of F. Closure of F is F itself, so we have to expand on that. And we try with EF. We find that the closure of EF is equals to EF and G, which is the entire table of R2, and so EF is a candidate key. Next thing, we find FG. FG implies FG and E, which is also all the attributes of the table number 2, and so EF and GF, both of them are candidate keys. So the prime attributes for table 2 is E, F, and G, and there are no non-prime attributes. It passes 2NF because E is prime. So once again, the criteria for 2NF is that for every non-prime attribute is fully dependent on the candidate key. So in this example, this is prime. So this will not be considered to violate because E is a prime attribute. Similarly, it will pass 3NF because E is prime, and so there is no. So over here, there is no partial so-called dependency because E is a prime number. Prime attribute. For 3NF, non-prime attributes depend only on candidate keys or super keys. So talking about transitive dependencies, same thing. It will not violate because E is prime, so you don't. So that criteria does not affect this functional dependency, but it will fail BCNF because G implies F, and G is not a super key. So BCNF will fail for this criteria. or rather for this functional dependency. Let's look at another example. So over here I have A, B, C, D, E, F, G, and AB implies CD, D implies F, C implies E, F implies C, B implies G, and I have A, B that is missing from my right hand side. Let's check. A, B is missing. I have a C, D, I have E, F, G. Okay, yeah, so AB is missing. So let's find the closure of AB. AB implies CD, so AB, CD. C implies E, so AB, C, D, E. DE implies F, so A, B, C, D, E, F, and B implies G, so A, B, C, D, E, F, G. So correct. A, B is a candidate key. And let's see. Okay, so I find that the maybe if you prime attributes A, B, non-prime attributes C, D, E, F, G, and so you find that the non-prime attribute of G is dependent on part of the candidate key B, and so this will fail the second normal form. Let's look at another example. R1 A, B, C, D, E, F, and I have A, B implies C, D, I have D implies F, C implies E, and F implies C. Very similar to what we have on top, but I think I remove one of it. And let's see, I have AB is the candidate key. So the prime, let's do a check. Yeah, it should be correct. Similar to this one should be correct. It's similar to what we have earlier on. So the prime candidate attributes are A and B, non-prime C, D, E, F. And so here we don't have this that violates the 2NF, and but we have a non-prime attribute that is dependent on prime attribute, on another non-prime attribute. So in fact all these three functional dependencies, they fail the third normal form. Okay, now with these examples, the next part of the lecture we will go into how do we construct both the third normal form, which I think is more important, as well as the B, C, and F. Finally, let's at last go on to the algorithm to construct your third normal form. The algorithm in particular we'll be exploring is called the Bernstein's algorithm. So there are three steps to this. So firstly, we have to check that all the functional dependencies, they are the minimum cover. Second thing, we create the new tables from the functional dependencies, and in the third step we try to combine them. So we are going to run through all the earlier examples we did where we check that it fails either the first normal form or the second, or rather either the second normal form or the third normal form. We're going to revisit it in this part, and then we're going to convert it back to, or rather we're going to find a way to convert it to the third normal form. And at the same time, after we do the conversion, we are also going to check that it will be both lossless and also preserving of all the functional dependencies. Yeah, so this is actually quite a important and relevant thing, even like so-called when you are designing database tables in the future, when you're working whatever. So you definitely will come across cases where you require to do things like this. So let's go on to the first example. So let's use the so-called slightly trivial example. There's a table of ABC. A implies B, B implies C. Step 1, we check whether is this a minimal cover or not. So yes, this to be a minimal cover. So yeah, you can't drop either one of them, and yeah. So step 2, from these functional dependencies, you create the new tables. In this case, table R1 will consist of attribute A and B. Table R2 will consist of attribute B and C. So yes, these will be the new tables that are created. We won't be able to, in a way, combine any tables. So usually I try to combine tables that share the same candidate key. So in this case, we won't be able to do it. So step 3 will there'll be no output from, we won't be able to do anything out of step 3. The thing we want to check is, so firstly, does it preserve functional dependencies? So with the algorithm, we are guaranteed to preserve all FDs, and for the simple reason, we are constructing the tables from the functional dependencies themselves. So of course, we will be able to retain all the FDs. And to do a check, A implies B. This A and B are present in R1. B implies C. B and C are present in R2. So yes, it will preserve all the functional dependency. The final thing you want to check is it a lossy decomposition or not? So we go to our table. We have attributes A, B, and C. We have table R1 and R2. We put the alphas, or we call them the variables, dependency variables on attributes A, B for R1 and B, C for R2. And we see that for the first FD, we won't be able to fire this off because there's only one dependency variable on row R1. For the second FD, we find that we are able to fire this off because they are it passes the first step. Firstly, there are two so-called dependency variables, both in row R1 and row R2, or table R1, table R2. That's number one. On the right hand side, there is at least one dependency variable, and that is on table R2, and there is one that is not a dependency variable on row R1. So we fire off this and we put on a dependency variable over here, and we realize that for this row, which pertains to table R1, we have all alphas here, which shows that this will be a lossless decomposition. Okay, let's go to another example. Okay, so this a slightly longer one. So I have A, B, C, D, E. The dependencies: A implies B, B implies C, D implies C, D implies B, and C implies D. Okay, so we first find the minimum cover. Is this set of functional dependencies the minimum cover? We don't know, so we can find out now. So firstly, we try to find whether are we able to drop any attributes or not. So we will not be considering this, and this. We will only consider this FD and this FD. So let's look at DE, which is on the left hand side. Are we able to drop either D or E? Looking at D, let's find the closure of D. The closure of D is D itself. It does not imply E, and so we won't be able to drop D. Let's look at E right now. The closure of E is also equals to only E, and so it does not imply D, and so we won't be able to drop D as well. And so both DE attributes, D attributes are required for both of these functional dependencies. That's the first thing. Second thing is, are we able to drop any functional dependencies or not? So let's and for this we have to go through one by one. A implies B. Let's assume that A implies B is not around, and let's see, are we able to recreate back A implies B from the rest of these FDs or not. So assuming A implies B is not around, we find the closure of A. Closure of A is equals to A and C and D. A, C, and D, and that's all. So there's no B, so this is required. A implies C, we assume A implies C is not around. We find closure of A. Closure of A is A, B, and that is all. And so this is also required. Let's find the closure of DE. Closure of DE is B, D, and E. There's no C, and so this is required. Let's find the closure of DE implies B. It will be C, D, E. There's no B, and so this is also required. Let's find the closure of C. The closure of C is C itself. There's no D, and so this is the minimum cover. That's the first step. Second step, we create the new tables from the minimum cover. So I have 5 tables over here. So consisting of A, B, which let's just underline the candidate key, DE, and D over here, and C. So these will be the new tables that are there. When in step 3, I like to combine tables with the same so-called candidate key. So I combine these two tables, R1, R2 together. Let's say I form a table P over here. So I have A, B, C with candidate key of A. I combine table R3, R4 here, and I have D, E, C, B. Oh, sorry, with a candidate key of D, E. Okay, so for this last table, I realized that C and D, they exists in table Q. So actually, this will automatically be subsumed in table Q, and I need not create a table R5. Okay, so now I've completed step 1, step 2, step 3. Let's check. So these are once again the functional dependencies. These are the two tables I created. I draw this dependency, this so-called I don't know what this is called, this table. I have A, B, C, D, E, table Q, P, and Q. Table P consists of A, B, C. Table Q consists of B, C, D, and E. So I'll try to see whether is this entire thing lossless or not. So let me look at A. A implies B. I won't be able, there's only one dependency variable at table P, so I won't be able to fire this off. A implies C is the same thing. DE implies C. DE, there's only one initially, so I won't be able to fire this off. DE implies B, so same situation. C implies D, so I have two dependency variables here. Pass the first test. One dependency variable of the right hand side on table Q, and I have one empty dependency variable on table P, and so I can fire this off. I have alpha 1 over here. I have to go through this all over again to check if I'm able to fire off any other functional dependencies. So none for this, there's only one. None for this as well, same thing. DE, unfortunately I can't fire this off. DE, nothing as well. C implies D, this is the same, and so this is a lossy decomposition. Okay, so we realized that Bernstein's algorithm is not lossless, but there is a way that we can do to guarantee this to be lossless. So the way to do it is that we will add another table in, and this new table is the candidate key of my original table over here. Okay? So once I add in the candidate key of my original table over here, it will guarantee my Bernstein's algorithm, the decomposition, to be lossless. So why intuitively is because, right, the candidate key of the original table already implies all the other variables already. So that will be the common table that you can do all your natural joins in, and it will guarantee that you are able to recreate back the entire original table from your decomposition. The functional dependencies will also be preserved because they are likewise created from your minimal cover. Okay, let's do it right now. So I will just the candidate key of the original table is AE. So I just add in this additional table AE over here. So I will have a new row AE here. What I'll do is I will go down these FDs one by one. I'll try to add in dependency variables. I look at the first one, A implies B. A implies B. I have two dependency variables here. I have one empty one here, so I can put in my alpha 1 here. Second dependency variable, A implies C. Same thing, I'm able to put alpha 2 over here. The third dependency variable, DE implies C. I can't do anything for now. D implies B, nothing as well. So C implies D. I have C. I have 3 dependency variables here. I have 1. I can put in both alpha 3 here and alpha 3 here. And so I have one entire row full of dependency variables, and so I can conclude that this decomposition is lossless. Does it preserve all my FDs? Definitely yes. AB is here, AC is here, DEC is here, DEB is here, CD is also here. So it preserves all my functional dependencies as well. Okay, let's look at a few more examples. This one, A, B, C, D, E, F, G. And this is my functional dependencies. AB is my candidate key. So first thing, what is my minimal cover? So yeah, so a bit irritating, but I need to do this. So first thing, are we able to drop any attributes on it from this? A, B implies CD. Are we able to drop A? What is the closure of A? Closure of A is A only, so I can't drop B. What's the closure of B? Closure of B is B and G. There is no A, so I can't drop A as well. So AB will have to be present in this functional dependency. D implies F. Can I drop D? Closure of D is D, and that's all. So I can't drop it. I can't drop E. What is the closure of E? Closure of E is E itself. So I can't drop D. So both of them will be required for this FD. Now, are we able to are we able to drop any functional dependency here? AB implies CD. I assume that this will not be around. I find closure of AB. Closure of AB is AB and G. And so I have to keep this. Closure of DEF is DE, and that's all. I have to keep this. Closure of C is C, and that's all as well. I have to keep this apparently. Yep. Closure of F is F. Yeah, that's all. Closure of B is B, and I think that's about it. Okay, so this is, I can't drop any of the functional dependencies, and so this is the minimal cover. Next thing, create a new table. So from every single FDs, I create a new table. I'll A, B, C, D, D, F, C, E, F, C, and B, G. Okay, I don't have any overlapping primary keys. Excuse me. So I'm going to just not do any combination, and I'll have 5 different tables. I will check whether is this lossy or not. I have A to G over here, R1 to R5 over here. I have alphas on my attributes in my respective tables. The first thing I do is I try to see whether am I able to fire off any functional dependency one by one. AB implies CD. AB, nope, it fails step 1, so I can't do anything here. DE implies F. DE, I have DE implies F. It fails the step 1, so I can't do anything here as well. CE implies C implies E. C implies E. So at last I can do something. I have 3 dependency variables here, and originally I only have 1 over here, or rather these 2 over here. So what I can do is I can add this dependency variable here, and this dependency variable here as well. So C determines E will have these 2 so-called dependency variables that appear. F implies C. Let's look at F implies C. Yeah, I have 2 functional dependency variables, and F implies C. Yeah, so actually I can do this. I can find this over. So I have 2 over here. So actually I can do. Yeah, so I can have something over here. Maybe I just terminate. Okay, so it doesn't make a difference to the final answer, but just for completeness, F implies C. Yeah, I should have something here as well. And B implies G. So B implies G will be I have 2 dependency variables here, 1 over here. These are used. I will have. So we went through 1 round of this already. Let's go through the second iteration. AB implies CD. AB implies CD. We won't be able to do anything new here. DE implies F. So DE will be this, implies F. So alpha 3 actually has not been filled up yet. We only fill up to alpha 2. So it means that we will be able to fill up alpha 3 at this step. Filling up alpha 3 at this step will give us 1 full row of dependency variables, and so we can then claim that this decomposition is lossless. Okay, let's go on to the next example. In the next example, I have A, B, C, D, E, F. It is in fact the same as this, just that I removed away this last FD. So the minimum cover will definitely be the same, and let's just do this. A, B, C, D. I will have this will form 4 tables: A, B, C, D, E, F, F, C, E, and F, C. What I will do is I will then have this table over here with A, B, C, D, E, F, 4 rows, R1 to R4. Fill up the alphas for my respective attributes. So A, B, C, D, D, E, F, C, E, and F, C. I'll go through this one by one. A, B implies C, D. A, B implies C, D. I can't fire this off. D, E implies F. D, E implies F. I can't do anything for now. Yeah, I think. C implies E. C implies E. C implies E. Yeah, C implies E. I actually can fill up this and this over here. So C implies E. I have 3 dependency variables fill up. I have 1 dependency variable over here. So yes, I will be able to fill up this and this. F implies C. F implies C. I will have 2 dependency variables here, 3 over here. I'll be able to fill up alpha 2 over here. So this is one iteration. Let's try to go through the next iteration. A, B implies C, D. A, B implies C, D. Can't do anything. D, E implies F. Oh, so now I can fill up F over here. I have alpha 3, and now I have 1 entire row of dependency variables, and I can now conclude that this decomposition is lossless. Okay, good. let's go to the next example. A, B, C, D, E. A, B, D implies C, B, C implies D, C, D implies E. And let's look at the following. Okay, what's the minimum cover in my step 1? A, B, D implies C. So I have to check whether can I drop A, can I drop B, can I drop D, can I drop yeah, so I have to check whether am I able to drop any of these terms from this or not. So yeah, you can try that, but intuitively you won't be able to drop anything. So you have to check the closure of A, the closure of B, the closure of D, the closure of AB, the closure of BD, and the closure of AD. So I have checked already, and yeah, you won't be able to drop any of the attributes here. Let's see whether are you able to drop any of the functional dependency. So ABD implies C. If you cover this, you won't be able to do it. And if you cover this, you won't be able to generate BC implies D as well. If you cover this, you won't be able to generate CD implies E as well. So this is the minimum cover. Step 2, you generate out the various attributes with the corresponding tables and the dependency variables. You realize that I am able to fire off CD implies E. Okay, so let's do step by step in case I make another mistake. ABD implies C, I can't fire this off. BC implies D, I can't fire this off. Yeah, all are filled up already. CD implies E, CD implies E, yep, so I fire these two off. I have one whole line for my dependency variables, and so this is a lossless decomposition. Okay, so the next thing that we'll be doing is, this is for decomposition into 3 and F. The next thing we'll be doing will be the decomposition into BC and F. Okay, the decomposition excuse me, into BC and F, the algorithm that is presented is pretty straightforward. So what you do is you pick the functional dependency that violates the BCNF so-called condition, and then you will decompose it to the first table, which is from the left hand side and right hand side, and on the right on the other table it is that of the left hand side with the rest of the attributes. You compute the functional dependencies and the key, and you repeat until all the tables are in BCNF. So that's basically about it. I will not be concentrating a lot on this, so we will not test on this, but I think it's good for you guys to know this method as well. So let's go into this. Decompose R1 into AB and the rest into A and the rest of it. So if I have A, B, C, D, E, F, the functional dependency is CD implies EF. The key is A, B, C, D. So the violating condition is CDEF. CDEF will be put into one table, and CD and the rest of the attributes, which is A, B, will be put into the other table. So that's about it. And now we have the so-called we have the two tables that are already in BCNF. Okay, another example. So A, B, C, D, E. The dependency A implies B, E, and C implies D. For this table, the candidate key is AC. This table is not in BCNF. It is neither is it in not even in 2NF. So what we do is we can both this and this, they violates the BCNF or the 2NF. So what you do is let's look at the first so-called FD first. We take A, B, E into one table, and we take A and the rest of it, which is C, D, into the other table. A, B, E is in one table, A, C, D is in the other table. you look at the functional dependencies, A implies BE and C implies D. So for this, my candidate key is A, and so excuse me, this is now in B, C, and F. Let's look at this, or rather this table. My candidate key based on this functional dependency is A, C. So this again violates the partial dependency of the 2NF, and so this is not in B, C, and F. So what we do is this FD violates it. So I take CD and put it in one table. I take C and the rest of it, which is A, put it in another table. And now these two are in B, C, and F, and now this decomposition is now in B, C, and F. Okay, so this turned out to be a pretty long chapter on normalization. Actually, practically, this is it actually is one of the very how to say, it is a topic that I have used in my real work before, I would say. Yeah, so it is very relevant. It's actually very important. So you may find that we are playing around with a lot of alphabets, but we really do decomposition like this when we are designing database tables. So I think and I mentioned this in the lectures before, we usually go up to 3NF. We don't go up to BCNF or 4. I mean, at least for me, I've almost never went up to BCNF or 4NFs before. 3NF is really good enough, and in fact, we really do plan our tables such that they meet at least 3NF. So I think this will be quite a valuable topic for you guys to learn and to understand. Hopefully, it'll be useful to you guys in the course of your career. Thank you so much.